In this video, I'd like to teach you how to derive the power rule for differentiating polynomials. So you might have learned that the slope of a function is just the rise over the run, which can also be written as rise is just change in y, or delta y dy, and run is change in x dx. So if you want to find the slope at, for example, this point here, let's call this point x. You might want to choose another point so you can find the change in y and the change in x relative to the 2 points. So let's pick a point here. This point here will be x comma y, and this point here will be x2 comma y2. There we go. So let's note that the change in x, so x2 minus x, let's call that change in x, so dx, right? So you might have also seen the slope of a function in the form y2 minus y1 over x2 minus x1, which is just your change in x. Now if you want the slope for this particular point, if you take a point that's really far away from it, you won't get the slope at this point. You'll just get the average slope through the function. So if you want the slope at this point, you want this point to be really, really close to this. So you might want to take the limit of y2 minus y1. Oh yeah, limit as your change in x approaches 0 of y2 minus y1 over your change in x. Now, oh yeah, sorry, we don't actually have y1. I called it y before. Okay. So what is y2? Well, it's just a function of x2, right? F of x2. So we can rewrite this. Actually, limit as dx approaches 0 of f of x2 minus y is just f of x. F of x all over your change in x. Now recall that x2 is just equal to x plus your change in x, right? Because we chose an x2 that's just a little bit of a distance from x. Actually, dx far from x. So we can rewrite this as your limit as dx approaches 0 of f of x plus dx minus f of x all over dx. So for example, if we had a function of, I don't know, f of x equals x squared. So let's try plugging that in. You get the limit of dx approaches 0 of f of this stuff. So we plug that into x here. So we'll get x plus dx all squared minus x squared all over dx. So if you expand this out, you get limit dx approaches 0 of x squared plus 2 times x times dx minus x, oh sorry, missed a term, plus dx all squared minus the original x squared all over dx. So you can see some things cancel out. For example, your x squared and minus x squared cancel out, right? That's just 0. And your dx terms in the numerator will cancel with the dx in the denominator. So this will cancel with this dx, and this will cancel with one of these dx's, leaving you with limit as dx approaches 0 of 2x, right? These two cancel, and this cancels with one of these. So you'll be left with dx to the power of 1. So 2x plus dx. Now since this is the limit as dx is approaching 0, your dx is going to be really, really close to 0. So it's probably not going to be significant when you're dealing with larger values of x. So we can just cancel that out. So you'll be left with your derivative of x squared will be just 2x. So derivative notation, whoops, dx of x squared equals 2x. Now this is just for the example of f of x equals x squared. What if instead we have f of x equals x to the n? So in this case, you would just do the exact same thing. Limit as dx approaches 0 of x plus dx to the power of n minus x to the power of n. Ooh, whoops. All over dx. So if you start expanding this out, you might want to check out the binomial theorem if you need help with that. But you'll end up with limit as dx approaches 0 of, and this stuff expands to x to the power of n plus n times x to the power of n minus 1 times dx, and then plus a bunch of stuff that you won't actually need. I'll show you why in a sec. I'll just write it out for now. So n squared minus n over 2, I think, x to the power of n minus 2 dx squared, all that kind of stuff, dot dot dot, and your last term is minus x to the n. And this is all over dx. Ooh. Excuse me. All over dx. So you can see some things that start to cancel. X to the power of n and negative x to the power of n will just give you 0. Now if you factor out a dx from the numerator, you're left with limit dx approaches 0 of dx bracket n to the power of n times x to the power of n minus 1, and you factor out the dx, so plus n squared minus n over 2 x to the power of n minus 2 dx, dot dot dot, a bunch of dx's. All these terms have dx's in them, and that will all be over dx. So these two cancel, and you're left with the limit as your change in x approaches 0 of n x to the power of n minus 1 plus all this junk. Now the reason that this stuff after the first term doesn't matter is that your change in x is approaching 0, and all these terms are multiplied by change in x after the first term. So they will all equal to 0. And all you're actually left with is that your derivative of x to the power of n, right? Your change in f of x over your change in x of x to the power, your change in x to the power of n over your change in x is going to be equal to n times x to the power of n minus 1. So that's the power rule for differentiation. The integral power rule can actually be derived quite easily from this. You can say here for derivatives we started with x to the power of n. Let's start with x to the power of m for an integral. Say you're integrating x to the power of n. So since you know that if you derive a function or differentiate a function and then you integrate it again, you should get the same value. So let's say, since this is n x to the power of n minus 1, and here we started with m, let's say that m equals n minus 1. So, oh yeah, and this should probably have a coefficient. Let's make it, this is n, so n equals m plus 1. So let's just add that on. M plus 1. So this should get you your original value of x to the power of n. So if m equals n minus 1, then you might want to add 1 to get it back to its original value of n. So you'll have to add 1, x to the power of m plus 1, and then you have this term in front of it that's m plus 1. And we didn't start with a term there, so you want to get rid of that. So you would have to divide by m plus 1. And that's the integration rule. So if you start with x to the power of m, you integrate, oops, that's not nice, integrate x to the power of m, you should get x to the power of m plus 1 over m plus 1. Let's box that in. Yeah. So that's just a short intro on deriving the power rule for differentiation and integration. Thanks for watching.